In this project, we are predicting individual medical insurance charges using demographic and health-related features. The target variable is charges, which represents the medical cost billed to each person. This is a regression problem because the target is a continuous numerical value. The dataset includes several key features. First, we have age, which is a numerical variable. Generally, medical costs increase as people get older, so we expect a positive relationship between age and the charges. Second is BMI, or body mass index, which measures body fat based on height and weight. Higher BMI is often associated with higher health risks, so it also tends to correlate positively with insurance costs. We also have the number of children covered by insurance. This is another numerical feature, and while it may influence total cost, its effect is usually moderate compared to other variables. Next, we have categorical features such as sex, smoker status, and region. Sex is encoded as 0 for female and 1 for male. Region represents 4 geographic areas. These variables may affect cost slightly, but in most analyses, their impact is smaller. The most important feature in this dataset is smoker status. It is encoded as 0 for non-smoker and 1 for smoker. Smokers typically have significantly higher medical expenses, and this variable shows the strongest correlation with the target. In both visualization and correlation analysis, smoker clearly stands out as the dominant predictor. Overall, this dataset represents a classic healthcare cost prediction problem. Age, BMI, and especially smoker status are the key drivers of medical insurance charges. By combining strong feature engineering with ensemble tree models, we can significantly improve prediction accuracy.
Now I will explain what we did to improve my regressor's performance. We mainly did 3 things. First, feature engineering. Besides the original variables, we created new features that better match real-world partners. For example, a smoker BMI age and BMI and smoker age capture how two variables work together to increase medical cost. And the age captures a nonlinear trend where cost may rise faster as age increasing. And we also attend binary filters like BMI high, BMI low, and age 30 plus, age 15 plus to make important thresholds. So the model can learn different partners in different range. And we also fix random states equal 13 to make the training design reproducible and to compare results fairly. Second, we use ensemble model to improve generalization instead of rely on one model. We trained multiple regressors such as several gradient boosting and random forest, and then combining the predictors. This help reduce variances and make the results more stable on new data. Third, we use automatic search for the best ensemble weight. As the first, we use the fixed manual weight like 0.4, 0.2, and we tried 0.5 and 0.1. Which is simple but may not be optimal. Later, we switched to an automatic mass, We run a grid search over many weight combinations on the validation set and choose the weight that gives the lowest validation RMSE. This let the data decide how much its model should contribute, and it usually performs better than fixed or average weights.
To assess and improve the fit of our regressor, we adopt a systematic evaluation strategy, combining quantitative metrics, diagnostic tools, and bias variance analysis. First, we used RMSE as the primary evaluation metric because it penalized large errors more heavily, which is appropriate for medical cost prediction, where extreme underestimation can be risky. Rather than relying only on training performance, we evaluated models on a validation set to measure generalization. Model selection was based strictly on validation RMSE, not training RMSE, to avoid selecting overfitted models. Second, we analyzed model behavior using learning curves. The curves revealed a persistent gap between training and validation RMSE, indicating moderate variance. This suggests that the model was somewhat overfitting rather than underfitting. Importantly, both curves were relatively low and stable, which confirmed that bias was not a primary issue. Therefore, improvement efforts focused on variance reduction rather than increasing model complexity further. Third, we evaluated the contribution of feature engineering by comparing validation RMSE before and after adding interaction and nonlinear terms. Interaction features such as smoker multiply BMI and smoker multiply age reduced validation RMSE, noticeably confirming that nonlinear risk application effects exist in the data. However, I also monitored whether these additional features increased overfitting, since tree-based ensemble methods can handle nonlinearities. Naturally, we ensured that added features produced measurable validation improvement rather than relying on theoretical assumptions alone. First, we compared individual models, like gradient boosting and random forest, with ensemble combinations. While individual gradient boosting models performed strongly, their errors were not perfectly correlated. By aggregating predictions, variance was reduced and validation RMSE improved. This demonstrated that the ensemble benefited from diversity among base learners. Instead of using manually assigned weights, we implemented grid search over weight combinations and selected weights, minimizing validation RMSE. This transformed the ensemble into a data-driven weighted averaging system rather than a heuristic combination. Optimized ensemble consistently outperformed equal weight and single model baselines, confirming that weight turning contribute to improved generalization. Finally, we critically assessed whether the model was well fitted. Although validation performance improved substantially, the learning curve still showed a moderate gap between training and validation error. Therefore, the model achieved strong predict accuracy but was not perfectly well fitted. Slight overfitting remained. Additional regularization, cross-validation, or early stopping could further improve robustness. Overall, model fit was assessed through quantitative comparison, learning curve diagnostics, and bias variance reasoning. Improvements were validated empirically rather than assumed, and ensemble design decisions were justified through measurable performance gains. This systematic approach ensured that model improvements generally enhanced generalization rather than merely increasing complexity. Thank you.